beat. It's a Madonna on the beat. It's a Madonna on the beat.
Temperature. The degree of heat of an object or the degree of heat at a place is known as temperature.
It's a
The
Madonna on the
Earth's
beat.
surface gets heated due to the heat of the sun. Hence, the air near its surface gets heated first. Then, layer by layer, the air becomes warm.
Madonna on the beat.
Hence, the temperature near the Earth's surface is higher and decreases as we go further away from the Earth.
It's a Madonna on the beat.
When heat transfer takes place without any medium, it is called radiation. You must have seen people sitting around the fire. Here too, heat is transferred in the form of radiation. In fact, every hot body radiates heat and becomes cold. Let's take an example of boiling water on a stove. From stove, heat conducts to pot as it is directly in contact. Due to convection, all the water particles receive heat. If you bring your hand very close to side of the pot, you will feel little hotness. This is because radiations coming from pot.
It's a Madonna on the beat.
The Sun and the Earth are determined by their temperatures. The Sun, which is very hot, emits high-energy shortwave radiation, while the Earth, which is much cooler, emits lower-energy long-wave radiation.
It's a Madonna on the beat. It's a Madonna on the beat. It's a Madonna on the beat.
Air always remains in motion. Sometimes it moves horizontally
It's a
and
Madonna on the beat.
sometimes vertically. The horizontal movement of air is called wind. Air moves horizontally from an area of high pressure to an area of low pressure. Thus, the air moving in a direction which is essentially parallel, horizontal, with the Earth's surface is called wind. The
It's a
speed
Madonna on the
of
beat.
wind is measured in kilometers per hour.
It's a Madonna on the beat. 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 It's a Madonna on the beat.
Understanding the basic concepts behind the development of pressure belts, we will not take into consideration the tilt of the axis and the influence of land-water distribution.
It's a Madonna on the beat.
The equator divides the globe into southern hemisphere and northern hemisphere, and equatorial belt extend up to 5 degree north and 5 degree south. Equatorial region receives nearly vertical rays of the sun, and this heats up the air near the equator. When temperature increases, pressure decreases. So, along the equator we have low pressure, and we call this region as equatorial low pressure belt. The warm air starts rising up in the troposphere, and as the warm air is rising, the temperature drops. After rising up to a certain point, it stops rising upwards because it becomes cooler and it is obstructed by tropopause. So, the air spreads out. The air starts moving in the southern and northern direction. As the air is moving, it becomes denser, and after a certain point, it sinks down to the surface. So, at around 30 degrees north and south, we have sinking air. This sinking air is cool air, so it forms high pressure systems. These regions are called as subtropical high pressure belts because these regions lie outside the tropical region and at the same time adjoining the tropical region. The sinking air now moves towards north and south. So, along the equator, the warm air rises, spreads out and cools and sinks down. In this way, it develops convectional currents. At the poles, the sun rays are very much inclined. So we have cold air that sinks. These regions are known as polar highs. In the northern hemisphere, the air moves towards the south, and in the southern hemisphere, the air moves towards north. At this point, we have air coming from north and south. So, at this point, the air converges and rises up. These regions are known as subpolar lows. So, at 60 degree latitudes, we have low pressure system because we have rising air. Along the equator, the air is rising because of convection, and at subpolar lows we have rising air because of convergence. This rising air also spreads out, cools and sinks. Same things happen in the southern hemisphere. On the surface of the earth, along the equator, the winds move from high pressure regions to low pressure regions, that is from subtropical highs to the equatorial low in the northern and southern hemisphere. These winds bend to the right in the northern hemisphere, and in the southern hemisphere the winds bend to the left, and this is described as Coriolis Effect. The winds bend to the right and left in the northern and southern hemisphere respectively, because the earth is spherical in shape and the earth rotates from west to east. In the same way, in between 30 and 60 degree north and south, the wind bends towards right and left in the northern and southern hemispheres respectively. Even at the polar region, the same phenomena can be seen.
Planetary winds are called by this name because they occupy an extensive area on the planet Earth. These winds blow all round the year. Planetary winds in different regions of the world are called the Easterlies, the Westerlies and the polar winds. A. Easterlies. The Easterlies blow from the mid-latitudinal high-pressure belt to the equatorial low-pressure belt. They generally blow from east to west. That is why they are called the Easterlies. B. Westerlies. The Westerlies blow regularly from the mid-latitudinal high-pressure belt to the subpolar low-pressure belt. In both the hemispheres, these winds blow from west to east. That is why they are called the Westerlies. C. Polar winds. Winds that blow from the polar high-pressure belts to the subpolar low-pressure belts are called polar winds. The direction of these winds is generally from east to west. The movement of air due to specific local conditions during certain periods are called local winds. Local winds blow within a relatively limited area. The effect of local winds is seen on the climate of the region where they blow.
Beat. It's a Madonna on the beat. It's a Madonna on the beat.
B. Land and sea breeze. During the day, the land in coastal areas gets heated faster than the sea water.
Madonna on the beat.
The air on the land becomes hotter and the air pressure becomes low. On the other hand, the sea water gets heated slowly and the air there is less hot.
Madonna on the beat.
Therefore, the air pressure is high. As a result, winds blow from the sea to the land. They are called sea breezes.
It's a Madonna on
At
the
night, the land cools down faster than the sea. the air pressure is higher on land. At the same time, the air pressure on the sea is low. Therefore, winds blow from the land to the sea. They are called land breezes. Land and sea breezes are seen only in the coastal region.
Master remark.
Mountain winds. During the day, air on the mountain tops gets heated faster. As a result, it becomes lighter and moves upwards. The air in the valley is not very hot. The air pressure is higher in the valley region than on the mountain top. Hence, wind movements start from the valley to the mountain top. These winds are called valley winds. At night, mountain tops cool down faster, whereas the air in the valley is warmer. As a result, the air pressure near the mountain top is greater than the air pressure in the valley region. Now, winds start blowing from the mountain top towards the valley. These are called mountain winds.
Master
Cools
remark.
approximately 1 degree Celsius every 100 meters. This is known as the dry adiabatic lapse rate. But that is not all. Cold air can contain less water vapor than warm air. So as the air cools below a certain temperature, it cannot retain all the water it initially had when it started rising. We say it becomes saturated, and droplets start to form. This leads first to clouds, and eventually to rain. The elevation at which this happens is known as the lifting condensation level. Because condensation causes heat to be released, as the air rises above this level, it keeps on cooling adiabatically, but at a much slower rate, since part of the cooling effect is offset by heat released by condensation. Eventually the rising air reaches to top. By this stage, it will have cooled down a lot, and likely it will have rained out all of its humidity, so we are now dealing with cold but dry air. Cold dry air is heavy, and it will start to sink, rushing down the mountain lee side. Now the opposite happens, the sinking air is under more pressure, it becomes compressed, and it warms up. By how much? Well, because the air is now dry, it will follow the dry adiabatic lapse rate, and warm up by 1 degree Celsius every 100 meters, or almost twice as fast as it cooled down, when it was wet, on the upwind side. By the time the winds reach the valley, they will be not only dry, but also warm.
Master remark.
know that water vapor is always present in the atmosphere. The amount of this water vapor is called humidity. The moistness or the dryness of the air depends upon the atmospheric humidity. Weather is said to be humid when the water vapor content in air is higher, and it is dry weather when the water vapor content in the air is lower. Rainfall depends on the level of atmospheric humidity. Rainfall is high in areas like Mumbai because it is near the Arabian Sea. It is low in areas which are far away from water bodies. From the water bodies like lakes, rivers, seas and oceans evaporates due to the sun's rays and form vapor. This vapor mixes with the atmosphere. It rises higher and higher along with the air. Due to the low temperature at higher altitudes, the water vapor gets converted into water droplets around dust particles. This process is known as condensation. These water particles float in the atmosphere. A collection of such minute water particles is known as a cloud.
fluffy cotton-like clouds. The name is from the Latin word cumulo, which means heap or pile. Cumulus clouds appear by themselves in lines or in clusters. Cumulus clouds can be formed from water vapor, super cold water droplets, or in ice crystals, depending upon the ambient temperature. They come in many subforms like altocumulus, cirruscumulus, stratuscumulus, and cumulonimbus. They are found in the lower level of clouds. Stratus clouds. These clouds look like gray blankets that hang low in the sky. When these clouds are near the ground or touching the ground, they are called fog. Stratus clouds are found in the lower level of clouds. If you see a stratus cloud and it's warm, there's a high chance of rain. But if you see a stratus cloud and it's cold outside, there's a high chance for snow. Like the cumulus cloud, it also has a lot of subforms, like the stratocumulus, stratonimbus, altostratus, and nimbostratus. Cirrus clouds. They look like wispy white streams in the sky. Its name comes from the Latin word cirrus, which means a ringlet or curling lock of the hair. They are the most common form of high-layer clouds. Cirrus clouds are most popularly known as mirror-tails. They can even form in the upper troposphere. Cirrus clouds are made of ice crystals. The only cloud that develops from cirrus is cirrostratus. Nimbus clouds. They are found in the lower level of clouds. But if the temperatures are cold enough, these clouds may also contain particles and snow. The sun or moon is not visible in nimbostratus clouds. The name nimbus in Latin means rain. Nimbus clouds often mean that a thunderstorm is brewing.
Due to the weight of your body, which you exert on the side of the boat. You must have read in your science textbook that any object has weight. Air also has weight. It is a highly compressible mixture of gases which applies pressure on the Earth's surface by exerting its weight. Thus, atmospheric pressure is defined as the pressure exerted by the vertical column of air lying above a particular area. Atmospheric pressure is measured by using a barometer. The unit of measurement of atmospheric pressure is millibar, written as MB. The variation in the atmospheric pressure from one place to another affects all weather changes. For example, the rising pressure makes the weather fine, while decreasing air pressure makes the weather cloudy and rainy. All these variations or changes in atmospheric pressure depend upon some factors. Let us know about these factors. Following are the factors on which atmospheric pressure of a place depends. 1. Temperature. 2. Altitude. 3. Density of the air. Let us discuss these factors one by one. 1. Temperature. There is an inverse relationship between air pressure and temperature. When the temperature of a place rises, the volume of the surrounding air starts to increase. This makes the air less dense. Due to the lower density, the air exerts a lesser pressure on the surface. When the temperature falls, the air becomes denser. That is, the weight of air increases. Due to the higher density, the column of air exerts a greater pressure on the surface. So, we can say that the hotter the place, the lesser the atmospheric pressure, and the colder the place, the higher the atmospheric pressure. 2. Altitude. Air is compressible and it concentrates near the Earth's surface. The upper layers of the atmosphere exerts more pressure on the lower layers on the surface of the Earth, thus increasing the density of air. Therefore, the atmospheric pressure near the Earth's surface is greater. As we move upwards from the Earth's surface, the air becomes lighter, which results in a low atmospheric pressure condition. This clearly indicates that the rate of atmospheric pressure varies inversely with height. 3. Density of air. The dense air is heavier than the thin air. Therefore, it exerts more pressure on the Earth's surface, while thin air exerts less pressure on the surface. The dense air is generally found near the surface of the Earth, especially at the ocean's surface. That is why we find more atmospheric pressure at the sea level than at the top of hills or mountains.
Shifting of pressure belts. A pattern of alternate high and low pressure belts exists over the Earth. These pressure belts are not continuous because the surface of the Earth is made of both land and water. Both get heated in different ways. Let's have a look at the 4 major pressure belts. The first pressure belt is the Equatorial low pressure belt that extends up to 5 degrees north and south of the equator. Being equator region, it receives direct sun rays and thus the air here is warm. This hot air expands, becomes light and rises. Hence, it creates a belt of low pressure. This is a region of calm air with very little wind and therefore it is also known as the doldrums. The second pressure belt is the subtropical high pressure belt that coincides with latitudes of 30 degrees to 35 degrees north and south of the equator. The air that rises at the equator eventually meets the tropopause where it can rise no further. It cools down as it rises and spreads outwards towards the poles, gradually cooling and sinking back down to the surface at about 30 degrees north and south of the equator, which causes an increase in air pressure. The third major air pressure belt is the subpolar low pressure belt around latitudes 60 degrees and 65 degrees north and south of the equator. It is created mainly due to the rotation of the Earth, which swings the bulk of the air towards the equator. These are areas of storminess, especially in winter. The fourth and last major air pressure belt is the polar high pressure belt located in the polar region. This belt is created because in this region the air is extremely cold and heavy, leading to a high pressure. Since pressure belts are caused mainly due to the temperature differences on the Earth's surface, they move in response to the migration of the sun. If the Earth had not been inclined towards the sun, the pressure belts would have been as they are. But it is not so, because the Earth is inclined 23.5 degrees towards the sun. On account of this inclination, differences in heating of the continents, oceans and pressure conditions in January and July vary greatly. January and July represents the winter and summer seasons respectively in the northern hemisphere. The exact opposite conditions prevail in the southern hemisphere. When the sun is overhead on the Tropic of Cancer, 21st June, the pressure belts shift 5 degrees northward. Whereas when the sun shines vertically overhead on the Tropic of Capricorn, 22nd December, the pressure belts shift 5 degrees southward from their original position. The shifting of pressure belts causes seasonal changes in the climate, especially between latitudes 30 degrees and 40 degrees in both hemispheres. In this region, the Mediterranean type of climate is experienced because of the shifting of permanent belts southwards and northwards with the overhead position of the sun. During winters, westerlies prevail and cause rain. During summers, dry trade winds blow offshore and are unable to give rainfall in these regions. When the sun shines vertically over the equator on 21st March and 23rd September, that is, during the equinoxes, the pressure belts remain balanced.
precipitation. The final process of hydrologic cycle is precipitation, through which water from the atmosphere falls down on the earth. In this process, the state of the water does not change, but there is only a change in its geographical location, that is, from the atmosphere to the hydrosphere, and from the hydrosphere to the lithosphere. This process takes place when tiny cloud droplets join together into larger rain droplets, become heavier, and fall to the Earth's surface through the atmosphere. Precipitation is classified according to its form in which it reaches the ground. The first type is rain, which reaches the ground in liquid form. Raindrops are 0.5 millimeters to 6.35 millimeters in diameter. Drizzle is the lightest form of precipitation, which occurs in the form of fine drops falling close together. These drops are less than 0.5 millimeters in diameter. The third type of precipitation is snow, which is composed of a powdery mass of ice crystals. Snow forms in extremely cold upper clouds. The fourth type is sleet, which is a mixture of rain and snow. When rain falls through a layer of cold air near the Earth's surface, raindrops get frozen into ice. Hail is the last type of precipitation. Hailstones are frozen lumps of ice produced by thunderstorms. They form inside tall cumulonimbus clouds, which are much warmer at the bottom than at the top, where the temperature is freezing. Air cooled to its saturation point will usually form clouds. But it does not always rain or snow when the sky is cloudy. Clouds give rain, but how a cloud made of water could float in the air was a question that puzzled scientists throughout the 19th century. Between 1911 and 1930s, scientists claimed that when ice crystals and water drops are mixed together in a cloud, the ice crystals grow at the expense of the water droplets. In such a case, the ice crystals quickly grow large enough to start falling, melt on the way down, and hit the ground as rain.
So the box, it's designed to contain some weather equipments like the thermometer and barometer. So the Stephenson screen, it's okay because it might on a question ask you why is it how it is, so tell us why it's designed this way. Well, you will say that it's white so that it can reflect sunlight. Okay? So that's the first kind of characteristic of it. It's white so it can reflect sunlight, and it has slats, so again these thingies, to allow air to circulate easily, so that the air can come in and stuff, and for the thermometers and stuff to work. So the Stephenson screen should be placed above the ground and away from the buildings. The idea is for the weather instruments to take accurate readings of the air rather than direct sunlight or heat from the ground or from buildings. So for more detailed information about the sighting of a Stephenson screen, so the location of a Stephenson screen in more detail. Well, basically, recap, it's a small weather station that is used to measure local weather conditions. A weather center will include a thermometer, so the maximum minimum, a hygrometer, which is a wet dry bulb thermometer, we'll go over these in a second, and a barometer. Outside the Stephenson screen there will be a rain gauge, an anemometer, and a wind vane. So, why is it designed like it is? Well, firstly, it's painted white so that it can reflect incoming solar radiation, so it can reflect light. It does not want to absorb heat because if it does, it won't give an accurate reading of the air. Also, it has a height above the ground, so as you can see it's placed on stilts, it's not on the floor. Why is this? Well, it should be above the ground at least 1.2 meters so that it does not receive heat released from the ground, because that would influence the measurements. Also, it has a roof to protect the instrument from precipitation, which is rain, because rain could affect temperature or humidity readings. Also, as you can see, it's in an open field, so it's away from buildings. This is to avoid any heat from buildings or any shadows from buildings, and the Stephenson screen should therefore be placed away from them. And the door of the screen should always face away from the sun. This means that in the northern hemisphere it should face north. And the screen has slats, like we said before, to allow air to circulate freely around the instruments, so the air can go in and go out. It's also in the open. It should not only be away from buildings, but also from trees and hills. This will ensure that air is allowed to circulate and that the screen is not in the shade. The screen should be twice the distance away from an object as the object's height. For instance, if a tree is 10 meters, then it should be 20 meters away. Also, you can see that it's on grass. To avoid reflection from white surfaces or absorption from dark surfaces, Stephenson screens are usually placed on grass. So a barometer. Barometers are used to measure air pressure. And it's measured in millibars. Just think of barometer, millibars. So barometers are normally kept inside Stephenson screens to keep them safe, because you can see they're pretty fragile, sensitive. And a barometer has a movable needle, so a pointer here. And the pointer can be moved to the current reading so that you can then make a comparison with the reading from the following day. Okay, so a maximum and minimum thermometer, sometimes called the Sixth thermometer because the guy who invented it was called Mr. Six. Okay, so basically a maximum and minimum thermometer records the maximum temperature of the day and the minimum temperature of the day. So you can use it to find the diurnal range, which means daily range of temperature. So a maximum minimum thermometer contains a mixture of mercury and alcohol. The mercury sits in the U-bend, so here, of the thermometer. The bulb at the top of the tube reading the minimum thermometer, reading the minimum temperature contains alcohol, and the bulb at the top of the tube reading the maximum temperature contains a vacuum. On the minimum side, the expansion of the mercury is restricted by the contracting alcohol, and on the maximum side, the expanding mercury can expand more freely into the vacuum. At any given time, both thermometers should record the same temperature. However, during the day, they would have recorded the maximum and minimum temperatures, and a steel marker should indicate these temperatures. So a wet and dry bulb thermometer. A hygrometer, which is another word for wet and dry bulb thermometer, measures the humidity of the air. Wet and dry, it's pretty straightforward. Because humidity is the amount of moisture, so water vapor, in the air. A hygrometer has two thermometers, a dry one and a wet one. Humidity is measured by using a table that looks at the difference between the wet bulb and the dry bulb. A hygrometer can also be used to find dew point. There is a difference between the dry and wet bulb thermometers because of latent heat created during the process of evaporation. So, anemometer. These measure wind speed. So as you can see, there are these little cups, and they turn around and it measures the wind speed. So, and it's normally measured in miles per hour or kilometers per hour, but can also be measured in meters per second. Digital anemometers, and then anemometers are very, very accurate, but the more basic plastic ones that many schools have aren't very good nor accurate at reading light winds. And anemometers, I can't even pronounce it, are normally placed on top of buildings so that they're not protected from the wind and so they don't experience channeling of wind. For instance, if an anemometer was placed in a corridor where wind was forced through, the readings would be higher than normal. Okay. Then we've got a wind vane. Wind vanes are used to check the direction of the wind. Compass points are used to give the direction that the wind is coming from, so we can see north, east, south, and west. And wind vanes are often placed on top of buildings so that they're fully exposed to the wind. When using a wind vane, you do need to use a compass to make sure that it's properly aligned. Okay, now we've got the rain gauge. Rain gauges are used to measure rainfall, and it's measured in millimeters. Rain gauges should be placed on grass, because if they're placed on concrete, extra water can splash into them because it's a hard surface and would therefore, make the water splash. Rain gauges should also be checked regularly to avoid evaporation. So how you would do it, you would dig a little hole in the earth, in soil, you put it in an open grass field, you would dig
So this is our manual rain gauge, and we've had a rain gauge on site pretty much like this one for the last 130 years. Every morning we have to come, take off the funnel, take the bottle out from inside which has been gathering the rainwater, and then pour it into a measuring cylinder just like this one. tells us exactly how much rain we've been having in the last 24 hours. So this is our tipping bucket rain gauge, which is the automated version of the rain gauge that I was just talking about. And it works in much the same way, funneling water through this part onto one side or the other of these buckets. And when an appropriate amount of water has fallen onto this side of the bucket, it tips. And then it starts to fall on the other side of the bucket. And same again, when an appropriate amount of rain has fallen, it will tip again. Each time the bucket tips, the computer knows that 0.2 millimeters of rainfall has been recorded. And that's how the system works. Really, really simple, very, very effective. And this is our instrument enclosure, technically known as a Stevenson screen. Inside here, we have a series of thermometers and temperature sensors. The reason why you have to have them in a slatted box like this is to keep the sun and the wind from having an effect on the temperatures. So when you see the temperature forecasts on the weather, they're talking about temperatures in the shade, or to be more technically accurate, in a box. We've had a Stevenson screen like this on site ever since 1882, and in here we have these two thermometers at the back. This one tells us what the humidity, the amount of water that's in the air. This one tells us what the air temperature is currently doing. This one tells us the maximum temperature in the last 24 hours, and this one the minimum temperature. But these days all of our thermometers are in fact backup systems for these guys at the back, which are electronic sensors, and they transfer data directly into the museum. This is the Campbell Stokes sunshine recording device, and it's been up here on the museum roof since the 1890s, and it's been changed every day by our front of house staff since then. Works by this glass sphere focusing the rays of the sun onto a specially prepared piece of card at the back, and it creates a burn mark. So as the sun moves from one side of the sky to the other, the burn mark moves from one side of the card to the other, and we end up with a trace telling us how much sunshine we've had every day.
Layers of atmosphere. Earth's atmosphere can be divided into 5 main layers, excluding the exosphere. The atmosphere has 4 primary layers, which are the troposphere, stratosphere, mesosphere, and thermosphere. Before going into main topic, we start from the Earth. Earth, our home. The Earth is the 3rd planet from the Sun. The Earth's distance from the Sun is 149,600,000 kilometers. Note: the distance from Earth to the Sun is called an astronomical unit, or AU, which is used to measure distances throughout the solar system. It is the only planet known to have an atmosphere containing free oxygen, oceans of liquid water on its surface, and of course, life. Roughly 70% of Earth's surface is covered by water, most of it in the oceans, and 30% of Earth's surface is land. Let's understand the layers of atmosphere. The atmosphere layers an important role in making life possible on Earth by protecting our Earth from harmful UV radiations of sun. The atmosphere of Earth is the layer of gases, commonly known as air, that surrounds the planet of Earth and is retained by Earth's gravity. There are 4 major layers of atmosphere above the Earth that are separated by temperature. Each layers are separated by an increasing or decreasing temperature of the gases in the layer. The first layer of atmosphere from the Earth is troposphere. Starting at ground level, it extends upward to about 10 kilometers, 6.2 miles or about 33,000 feet above sea level. We humans live in the troposphere, and nearly all weather occurs in this lowest layer. Most clouds appear here, mainly because 99% of the water vapor in the atmosphere is found in the troposphere. Air pressure drops, and temperatures get colder as you climb higher in the troposphere. The next layer up is called the stratosphere. The stratosphere extends from the top of the troposphere to about 50 kilometers, 31 miles, above the ground. The infamous ozone layer is found within the stratosphere. Ozone molecules in this layer absorb high-energy ultraviolet (UV) light from the sun, converting the UV energy into heat. The stratosphere actually gets warmer the higher the trend of rising temperatures with altitude. That means air in the stratosphere lacks the turbulence and updrafts of the troposphere beneath. Commercial passenger jets fly in the lower stratosphere, partly because this less turbulent layer provides a smoother ride. The jet stream flows near the border between the troposphere and the stratosphere. The third layer of the atmosphere is Mesosphere. It extends upward to a height of about 85 kilometers, 53 miles, above our planet. Most meteors burn up in the Mesosphere. Unlike the stratosphere, temperatures once again grow colder as you rise up through the Mesosphere. The coldest temperatures in Earth's atmosphere, about -90 degrees Celsius, -130 degrees Fahrenheit, are found near the top of this layer. The air in the Mesosphere is far too thin to breathe. Air pressure at the bottom of the layer is well below 1% of the pressure at sea level and continues dropping as you go higher. The Thermosphere or Ionosphere is directly above the Mesosphere and below the Exosphere. It extended up to 700 kilometers, 440 miles, above our planet. The Thermosphere absorbed high-energy X-rays and UV radiation from the sun, and atoms turning them into ions with a positive charge. The temperature of the Thermosphere varies between night and day and between the seasons, as do the numbers of ions and electrons which are present. The ionosphere reflects and absorbs radio waves, allowing us to receive shortwave radio broadcasts from other parts of the world. Temperatures in the upper thermosphere can range from about 500 degrees Celsius, 932 degrees Fahrenheit, to 2000 degrees Celsius, 3632 degrees Fahrenheit, or higher. The exosphere is the outermost layer of Earth's atmosphere. It extends from the exobase, which is located at the top of the thermosphere, at an altitude of about 700 kilometers above sea level, to about 10,000 kilometers, 6,200 miles, 33 million feet, where it merges into the solar wind. This layer is mainly composed of extremely low densities of hydrogen, helium and several heavier molecules including nitrogen, oxygen, and carbon dioxide, closer to the exobase. The atoms and molecules are so far apart that they can travel hundreds of kilometers without colliding with one another. Thus, the exosphere no longer behaves like a gas, and the particles constantly escape into space. These free-moving particles follow ballistic trajectories and may migrate in and out of the magnetosphere or the solar wind.